Welcome to today's podcast. We're going to be talking about the Wittig reaction. Specifically, we're going to be looking at the reaction, the mechanism, and the selectivity. The Wittig reaction starts with carbonyl, usually an aldehyde or a ketone, and a phosphorus ylide. Here's a genetic reaction. What results is a alkene. The phosphorus ylide, here shown as C6H5. This is just shorthand for a phenyl group. We'll look at the phosphorus ylide equilibrium in a second, but first let's explain the phosphorus component. This could have also been shown this way with 3 phenyl groups on the phosphorus ylide. For even further shorthand, I'm going to be using the pH for phenyl. So what we have on the screen now is just 3 ways to show this. Okay, so we're going to be taking a ketone, in this case, or aldehyde, and creating a alkene. The phosphorus ylide could be shown as the double bond through the carbon, but this is in equilibrium to the phosphorus ylide, where the phosphorus is shown as positive and the carbon is shown as negative. The synthesis of the phosphorus ylide starts by synthesis of the salt. We'll take the triphenylphosphine, react that with most often a primary halide. Again, this is going to occur through a SN2 type process, so therefore having less substituents on the backside, as we see the phosphorus lone pair attacking the antibonding orbital of the carbon, the leaving group, the halide in this time leaving. This is going to make a new bond between the phosphorus and the carbon. So the phosphorus gave up its electron, so it is positive. The halide leaves and actually forms the salt. So we end up with the phosphonium salt in the first step. Once we've done this, what we need to do is eliminate one of the protons. So the next reaction is reacting the phosphonium salt with a base. Of course, we're going to need a strong base. Normally this means a lithium base, and for this one we're going to use the CH3, the butyl lithium, the CH3, CH2, 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 and I'll show this fashion. Strong base is going to pull the proton off of the carbon. That's going to then result in our phosphorus ylide. And of course that can be shown as the double bond species that we saw in the previous slide. The mechanism is still under investigation, but there are two standard mechanisms that are shown. I'm going to start with the two-step because I think it better illustrates the nucleophile electrophile nature of the process. If we look at, again, our generic ylide, we have that reacting with our carbonyl species. Okay. For clarity, I'm going to go ahead and draw that with the carbon and the CH3s here. The anion of the carbon is going to be our nucleophile. Nucleophile attacks the electrophilic carbon of our carbonyl. Lone pair leaves. This is going to give us the carbon-carbon bond. Now the oxygen has an extra electrons. Since the pi bond was our leaving group in the first step, at this point then the oxygen would react with the positive phosphorus, giving us this four-membered ring system. At this point, then we're going to get a rearrangement of these electrons. Turns out that phosphorus and oxygen make a very strong bond, so therefore we can think about this four-membered ring reacting in the fashion to where the oxygen electrons are going towards the phosphorus. The carbon-phosphorus bond is breaking, those going towards the carbon. Of course, the carbon-carbon bond is going to be very stable, and that will take us to our final product, which would be then the double bond, the alkene, which we are focusing on since of course this is organic, plus then the trinyl phosphorus double bond oxygen. Okay. And again, this is a two-step process. This is a very standard two-step mechanism for the Wittig reaction. We also can have a mechanism that goes through a one-step. The one-step would be, of course, considered concerted. If we look at the one-step mechanism, instead of having the carbon nucleophile react with the carbonyl in the first step and then waiting, we're going to get both sets of electrons moving at the same time. So that would be going there, this coming here. That then would end up giving us our four-membered ring system. Then at this point, then we get the rearrangement. Oxygen-carbon bonds going towards the phosphorus. Now, both of these mechanisms have been proven to be correct. It may depend on what type of phosphorus ylide, depending on which one is most likely to be occurring. it actually turns out the type of phosphoryl ends up giving us our selectivity for this reaction. So again, if we go back and look, we can have the two-step process where first we get the carbon nucleophile reacting with the electrophile and the lone pair leaving, and then our phosphorus reacting with our phosphonium, and then just a rearrangement. Or we can think about having a one-step process to get this.